Hello and welcome to this video for physics. This video is going to focus on radioactivity, and specifically it's going to focus on the activity part. Okay, so we've got a question here that says a teacher used a Geiger Muller tube. So a Geiger Muller tube, as I've symbolized down here, is a tube like this, and it clicks every time ionizing radiation enters it. So remember that ionizing radiation is radiation that causes ions from atoms. So things like alpha, beta, gamma. So let me make a little note of that actually. So ionizing radiation. Radiation. E.g. So we've got alpha, beta, and gamma. Yeah. Yeah. And they enter this tube which clicks, okay, and that's your count. And we're measuring the number of counts in 60 seconds from a radioactive rock. So a radioactive rock like this that I've drawn here. So from this rock, we might get radiation as alpha, beta, or gamma, and to symbolize that, I'm going to draw a wavy line, which is for gamma, and then a straight line, which would symbolize the particles, a straight arrow. In addition to this, whenever we've got radiation that we're measuring with a GM tube or Geiger Muller tube, we will have radiation coming from the background, okay? So, for example, from the air or other sources like bananas, things like this, there will be other background radiation, and from the sun mainly. Okay, so we'll symbolize this background radiation. I'll draw this in, let's draw another color actually, so let's select yellow, for example. So let's draw this background radiation in with our yellow pen. Okay, and that's entering the tube as well. Alright, now let's go back up to the question. So we've got our Geiger Muller tube. Now we know that is a thing that counts ionizing radiation, so it makes a little click. Okay, we know that ionizing radiation forms ions from atoms. There's three types, alpha, beta, and gamma, that we care about in this situation. Yeah, and it measures the number of counts in 60 seconds, okay? So we've recorded 819 counts in 60 seconds, but the background radiation count was 0.3 seconds, alright? Calculate the count rate for the rock. Now remember, with a rate, a rate is something that's per second, okay? So I'm going to write that on there. So a rate, that's something that is per second. So whenever we've got a rate, we know, or we're trying to find out a rate, we know that we've got a number. So, for example, if we're using distance, it will be meters per second. That would be the rate. Yeah, but this time we've got counts and seconds, so it would be counts per second. So what we need to do to calculate the rate will be 819 per second, okay? So 819 divided by 60 even, okay? But what rate will that give you? Will that give you the rate of the rock, count rate for the rock, the count rate for the background, or the count rate for both? Now the answer is that's going to give you the count rate for both, right? So I'm going to say that that's our total. So I'm going to zoom in here. I'm going to write down the total count rate. So the total counts rate will be equal to 819 divided by 60, yeah, which will equal 13.65. Okay, so that's our total. Now to get the radiation from the count rate from the rock, which is stated in the question, calculate the count rate for the rock. Why did that happen? Yeah, what we need to do is we need to do, so count rate for rock. We need to do the total minus the background of, let's say, radioactive rock. It's going to equal total count rate minus the background. Okay, and this is true for any question you get like this. They like to say, calculate the count rate of an object, and you always have to remember to take away the background radiation. All right, and that is going to equal 13.65 take away, let's check our number. So 13.65 I got from the total count rate, yeah, which was just here. I'm not sure why this doesn't work. No, 13.65 was here, and the background radiation was 0.3. Okay, here. Oops. So I'm going to do 13.65 take away 0.3. 0.3. Okay, and that is equal to 13.35. Okay, and I'm going to put that over here. So 13.35. Okay, and that is our answer for that section. I did that quite comprehensively. I could have done that very quickly. Part B, we've got a household is worried about the radiation emitted by the granite worktop in his kitchen. Okay, so 1 kilogram of granite has an activity of 1,250 becquerels, and the kitchen worktop has a mass of 180 kilograms. Calculate the activity of the kitchen worktop in becquerels. Okay, and this is just a ratio question. We know that 1 gives 1,250. What's 180 going to give? Okay, so let me write this out. So 1 kilogram of granite equals 1,250 gross. Yeah. So 180 is going to equal 1,250 times 180, which equals 2,250. Okay, 225,000. That's going to be 225,000. Okay. Now, let's move on to part C. So part C, the average total radiation dose per year in the UK is 2 millisieverts. Okay, and sievert is the unit we use to measure radiation dose. Okay, maybe I'll make a little note of that up here. So sievert. Which is SV, that's the unit, equals the unit of radiation. Let's write that down there, of radiation dose. Okay, so if we're looking at millisieverts like in the question, we know that that is 0.00 whatever, yeah? 0.01 sievert will be a millisievert. Okay, so the table below shows the effect of radiation dose on the human body. And So here's our table. We've got 10,000 gives immediate illness, 1,000 gives radiation sickness, and 100 gives evidence of causing cancer. Okay. Now the average radiation dose from the granite worktop is 0.003 millisieverts per day. Okay, so we can highlight that. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop. So it's yearly. Okay, so if we're looking at per day and yearly, that should give some alarm bells is what we have to do, right? So if 0.003 in one day, and we know that there's 365 days in 1 year, to get the dose over 1 year, then we'll do 0.003 times 365 days, okay? So, dose per year equal 0.003 millisieverts times 365, which equals 1.095 millisieverts, yeah? Okay. So that's his dose per year. But we have not finished the question yet, because the question says explain why he should not be concerned. So, looking back at the table, when should he be concerned? He should be concerned if his radiation dose in millisieverts is equal to or exceeds 100. Now for our example, we have 1.095 millisieverts in 1 year. This is far less than the 100. So we can make the assumption, that because 1.095 is far less than 100, that the homeowner should not be worried. Okay? So now, let me just get rid of that. Let's move on to part D. So part D, bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. Suggest one reason why the banana equivalent dose may help the public be more aware of radiation risks. Now before this video, I'll be surprised if you knew what the sievert was. So why do you think that people may want to change the unit from sievert to banana equivalent dose for everyday people? Say you're speaking to your mum and dad and you said, you know what, this banana gives this many sieverts. Are they going to know if that's good, if that's bad? They're not. However, if you say, you know what, this banana gives this amount of radiation. Part D. So bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. Suggest one reason why the banana equivalent dose may help the public be more aware of radiation risks. Okay, so this is to do with familiarity, right? Now, how many people in the street do you think are familiar with sieverts compared with how many people you think are familiar with bananas? Most people understand that bananas are radioactive, and they'll be aware that the dose from bananas is not detrimental. So, the reason why the banana equivalent dose may help the public be more aware of radiation risks is because people can compare a radiation risk to the dose from eating bananas, right? They're more familiar with it. Let's go ahead and zoom in and write that answer in. So people can compare a radiation risk to the dose from eating bananas. Okay. And that concludes our video.